Hi, Miss Liu. Today I'll be explaining how to solve this polynomial with the rational root theorem. So first, you have to find the p and q, like the ratio of p and q, like p over q, and you have to find the factors. So in this case, p should be the constant, and q should be the coefficient of the highest degree. So the coefficient of the highest degree in this polynomial is x to the power of 8, and the coefficient's 1. And the constant here is, I'm not reading that, is this. So p is equal to negative that number. And if you put it in p over q format, it's like this. And here I listed all its factors, but in the next step of the rational root theorem, you only need to there's only a certain amount of roots that actually works in these number of factors. So you kind of just have to try and plug it in and do it. But in this case, I already know what my roots are, so that's easier for me. So I tried using -2 in synthetic division to test for the roots. And I could use any of these numbers. It's just that I'm not sure if it would give me a remainder of 0. Because the thing is, if there's a remainder of 0, that means that it's an actual root. But if there's a remainder of something that's not 0, it's probably not a root. And now that I have my whole polynomial in synthetic division form, I have to flip the sign when I write it down, because whenever you do synthetic division, you always flip the sign before doing the whole process. And so it's x plus 2 times this whole polynomial. And keep in mind that when I do this, the degree used to be 8, but whenever I do synthetic division, the answer always goes down a degree. So then I have to simplify this again, because I can't solve for x yet. Because for x to be solved, most of the time, it's either a trinomial, where we can solve by quadratic formula, or it is squared, where in that case we could solve for the square. And basically what I did here is that I did the first step for rational root theorem again, where I identified the p and q, which is this, over 1 again. And I listed some of the factors. I didn't list all of them because it is just a lot of numbers here, and you won't use all of them. So I listed most of some of the factors, and I tried doing it with 9, and actually -9 in this case. So I plugged in -9, and this is the polynomial I got, and I know this is probably the right root because the remainder is 0, so that tells me that that's a root. But now that we have this smaller polynomial than this one, we still can't solve for x because the degree is still too big. So we plug it into synthetic division again, and basically this is the answer I got. Remember to keep the binomial, because sometimes I forget, but remember to keep the binomial even after the second step, and this is the answer. And I perform my p over q, find the factors again, and this time I tried doing it, testing it with 1 in synthetic division, and this is the polynomial I got. I know it's a root because, again, 0, remainder, and this is the answer I got. So still can't solve for the x yet because the degree of 5 is still a really big degree. So we just keep on simplifying it, simplifying this one. So p over q again, p is 648, q is 1, and these are some of the factors. It's not all of them, but it's just some of them. This time I tried -9 again, and I know that this polynomial they give me is a root because, again, 0. But looking at the polynomial here that we got at the end result, it's still a degree of 4, so we still have to do rational root theorem again. Oh, but in this time, since there are 2 repeating binomials, which is x plus 9, they repeat twice, we simplify them by putting them in square root. And you have to now you again simplify. So p over q, I tried using 9 again, well, -9 again, and I know after I simplify with synthetic division that this is a root because it gives me a remainder of 0. And now finally, this polynomial is small enough for me to factor it, and how I can factor it is grouping the 4 terms. So first I grouped the repeating binomials here, like this, and then I also grouped I used grouping of 4 terms for this binomial, not binomial, polynomial, and this is what I can factor out from 2 of the terms, and basically this is what I get. And after I simplify this process here, I get this answer, but that's not it. I got this answer, but that's not it because I still have to solve for x, find the x equals 0 thing, and this is what I get. Basically, for each binomial, I set it to 0, and I solve for x, and these are the answers I got. I got a imaginary answer, which is x plus or minus 2i, and this makes sense because the original equation has a degree of 8, and the roots appear a total of 8 times. There are not 8 roots, but it appears in a total of 8 times. See, 1, 2, 3 for x plus 9, x plus 2 twice, x minus 1 it's just once, and for the imaginary root, it appears twice because plus or minus. And to further back my point, this is a rough graph of the polynomial we initially had, which is this. It is very long, so I will not read it. It is this. And the multiplicity, I'll just mention the roots first. The roots are -9, -2. There's an imaginary root, so it's not pictured on the graph, and 1. The multiplicity is 3, 2, 2, and 1. The roots, as I mentioned earlier, -9, -2, and 1 are rational, and the imaginary is plus or minus 2i. The end behavior is that as limit of f of x, as x approaches infinity, f of x approaches infinity as well. And as x approaches -infinity, f of x still approaches infinity. The domain is from -infinity to infinity, And the range, it's kind of a rough guess because Wolfram Alpha doesn't give me the precise number, but the graph starts here. Like the lowest, it doesn't start here. Like the lowest point the graph goes is around 120k with like in the y coordinate, and that's like the lowest point, and from there it kind of just goes on forever upwards. And the relative maximum is -9, 0, and -2, 0. Relative minimum is approximately -6 and 120k, and 1 and 0. So yeah, this is the end. Thank you.